The next few videos are about stratigraphy and relative dating. Relative dating is trying to figure out how old a feature is, such as a rock unit, relative to another feature, maybe a fault or a dike intruding across that rock unit. We're going to learn a number of principles that will help us decipher these kinds of puzzles. This image here is a great example of a number of geologic features that have occurred from the past to the present, and we have to figure out what happened first, second, third. We'll come back to the answer to this one later on, but let me at least point out some of the features that are here. We'll notice that there's a rock unit that has a folding pattern. And whenever we see a folding pattern in rocks like this, we usually think of them as metamorphic. There's another rock unit here labeled B that seems like an intrusion that came in as a magma chamber and solidified against this metamorphic rock unit. Above these two units, we see this squiggly line that sort of indicates a layer of erosion, followed by the deposition of a rock unit C, which has layers, it's probably sedimentary, and rock unit E, which is also probably sedimentary. There are a number of other features here. There are two faults. One of them comes through here on this side. Another one cuts through here over on the left side. And then there's also a dike, an intrusion of magma that has solidified and cut through some of the rocks. So this is the kind of puzzle we're going to try to solve. Here are the Unit 8 sea level outcomes. Please pause the video and write them down. Stratigraphy is the study of rock layers, which we call strata. Stratigraphers examine the order and position of these strata and try to figure out which came first, which came second, which came third, etc. They also try to tie it to the geologic time scale where we have absolute numbers for various features. Relative dating involves putting geologic events in order, typically from oldest to youngest, using a number of relative dating principles. To summarize, relative dating is a system of reasoning that's used to determine the chronologic order or sequence of a series of geologic events. Radiometric dating or absolute dating is using radioactive decay of radioactive isotopes to calculate the chronologic age of a rock. For example, with absolute dating, we could say this volcano erupted 283 million years ago. With relative dating, we wouldn't be able to say how long ago it erupted. Here's an analogy. The left-hand column shows a number of armed conflicts or wars from most recent to most distant in the past. Notice that we do not know when these events happened or how much time was between each of them. We simply know the order of them. For example, World War II occurred before the Korean War. On the right-hand side, we have the dates of these events. Notice that they're still in the same order from oldest to youngest, but now we have quantitative information about when they occurred and how much time was between each event. So relative dating in geology is like the column on the left. Absolute or numerical dating is like the column on the right. I'm going to talk about 7 stratigraphic principles that we use in relative dating. We'll start with the concept of uniformitarianism. James Hutton came up with this idea. He's sometimes called the father of geologic time. He was a Scottish geologist who proposed that geologic time was indefinitely long. And this was during a time when people were not sure if the Earth was even more than a few thousand years old. He formulated the principle of uniformitarianism, and below is a quote from him. We find no vestige of a beginning, no prospect of an end, when he's talking about geologic time. Uniformitarianism is often phrased as the present is the key to the past. In other words, processes that we observe today operated in the same way in the geologic past, and so if we look at modern processes, it can help us understand ancient events. For example, on the left-hand figure here, we have some footprints of an animal made in some sand. On the right hand, we have some dinosaur footprints preserved in a sandstone. And you can see these are quite big relative to the people here. What uniformitarianism tells us is that these footprints were not formed by dinosaurs walking on sandstone. They were formed by dinosaurs walking on soft sediment, like we see to the left, and that sediment was eventually turned into a solid sandstone. Another example includes ripple marks. On the right, we see a rock with ripples preserved in the upper surface. In the upper left, we see ripples of sand in a modern environment. Ripples indicate shallow water, so we infer that this rock on the right formed in shallow water conditions. Now you might think that all of this is pretty straightforward. Processes that are happening today are what happened in the geologic past. However, there's another idea that's a little bit different in terms of how the landscape on Earth has formed and changed over time, and that is called catastrophism. Catastrophism suggests that things in the past happened abruptly, large dramatic events. For example, worldwide floods that laid down all the rocks, or cataclysmic earthquakes that raised all of the mountains. Uniformitarianism is more of a small-scale continuous process. Erosion, deposition, uplift of mountains, all of these things take millions and millions of years and happen very slowly, very gradually. The principle of superposition. This is pretty straightforward. This says that rocks form from the bottom to the top in layers. So the rocks on the bottom are the oldest, and as you go up, the rocks are younger and younger and younger. And this is shown in the little cartoon to the right, and also in this shot of the Grand Canyon to the left. The lower rocks are oldest, then we have some younger rocks above them, and younger still rocks at the very top. Where do you think the oldest rock units are in this picture? That's right, on the bottom. The principle of original horizontality states that when rocks are formed as sediments, they are formed in large horizontal sheets. And if they are buried and turned into rocks, we then have large horizontal layers, such as shown here dissected by a stream. Here we see the Grand Canyon on the right, which shows an example of these horizontal sedimentary layers. Take a look at these layers. They're not horizontal anymore. You can see that they're slightly tilted, and then there's a sharp bend, a fold. What do you think happened first? That's right. First we have to deposit the rocks, and then we can fold them. Next we have the principle of original lateral continuity. This basically says that those large horizontal sheets of sediment can extend laterally for great distances. Here we have the Grand Canyon, and I've labeled some of the rock units. In this close outcrop we have the Hermit Shale, overlain by the younger Coconino Sandstone, and overlain by the youngest Kaibab Limestone. If we look across the canyon, we see these exact same units, the Kaibab Limestone on top, then the Coconino Sandstone, and then the Hermit Shale. And then there are other rocks that are even older below it. So this is showing how these rocks are laterally continuous across the Grand Canyon. But in fact, they go even farther. If we look at this cartoon, we can see the Grand Canyon shown here, and then these sedimentary rock units are shown here in sort of a cartoon fashion. And these can be traced as far north as Cedar Breaks and Bryce Canyon in Utah, over 100 miles away. So definitely a good example of laterally extensive horizontal sheets of rock. The next principle is cross-cutting relationships. This one states that younger features cut across older features. So faults, dikes, erosion must be younger than the material that is faulted, intruded, or eroded. On the left we have some sedimentary rock units, a blue, gray, and yellow unit. Then we have magma that's come up through those units and created a volcano. Eventually the magma source stops, the volcano stops building, and then we have erosion. On the right-hand side, this might be what's left after millions of years of erosion. So if we're walking along and we see this gray unit and then we see this dike, we know that the dike is younger than the gray unit because it cuts across it. Here's a fault that cuts across some rocks. Which one happened first, the faulting or the deposition of the rocks? You got it. First you have to deposit the rocks, and then you can fault them. Pause the video for a second and take a look at this fault and see if you can figure out what kind it is. It is a normal dip-slip fault. Here we have a mafic intrusion shown in the dark rock and a felsic intrusion shown by the light rock. Which one is older and which one is younger? It turns out the mafic intrusion is a dike that intruded into the felsic rock, so the mafic rock is younger. The principle of inclusions. Inclusions are rock fragments that are found within another rock, and those inclusions are always older than the rock in which they're found. One example is an igneous xenolith, and this is shown in the left photo. The dark colored rock right here is within this speckled colored rock around it. And what probably happened is that this speckled colored rock is igneous, and it was a magma chamber, and it was intruding into surrounding rock. Sometimes we call that surrounding rock country rock or wall rock, and sometimes pieces of it fall into the magma chamber. That's what happened here. This darker rock was part of the surrounding area. It fell into the magma chamber. The magma cooled and crystallized, and now it is a foreign rock or xenolith inside a younger rock. Rubble that is created from weathering of rocks that is then incorporated into new rocks is also older. Here's a cartoon showing both of these. Here we have three sedimentary units, brown, blue, and yellow. And then we have what's called a sill that intruded between the rock unit layers. Just like dikes, sills cut through pre-existing rock, but sills tend to form horizontal units parallel to bedding. We see that the sill has inclusions from the rock above it, and by the principle of inclusions, that means that the sill must be younger. On the other hand, on the right-hand side, we have the brown and blue units. Then we had a lava flow, and then we had the deposition of the yellow unit. The yellow unit has pieces of the lava flow in it. So once again, the principle of inclusions tells us that these pieces of lava flow in this yellow unit are older than the yellow unit. Finally, the principle of baked contacts. When magma intrudes rocks, it sometimes bakes the zone where it's contacting the rock. This is shown here with this slightly lighter color around this pluton, which is a solidified magma chamber. Here's a real picture of a baked contact. We have a rhyolite flow here that's about 5 to 10 million years old. The old ground surface was right along here. Then about 1 million years ago, a basalt flowed over the surface of this rhyolite. And the heat of that lava flow baked the rhyolite to turn it this kind of reddish color at its top margin. We will stop here, and in our next video, we will look at this diagram again and figure out the order of events.